Let's look at application on how array is utilized. Um, that example is the natural language processing. Natural language processing basically means you how to process and analyze large amounts of natural large language data, like words. Like it looks for patterns in words and documents and try to do speech recognition and understanding of a natural language. For example, if I say, Alexa, how do I learn Java programming? This is what I'm talking to the Amazon Alexa. Then Alexa should be able to understand what I'm looking for, what I'm asking for. And she should reply, you can take Professor Shen's class, right? So in addition to language understanding, it also need to, she or it also need to generate a language, a combination of natural language tokens that makes sense in natural language. So this is several parts: speech recognition, natural language understanding, and natural language generation. So this sounds very advanced and very fancy. And everybody is using iPhone or AWS Alexa these days. And this looks almost like a magic in a sci-fi movie where you say something and the computer understands you. But down the hood, how do you do? How do you achieve this? You can achieve those pretty much follow the same simple operation on arrays that we have been doing. An example is like the Baconian theory of Shakespeare authorship. This is a theory says that Sir Francis Bacon, who is a philosopher and a scientist, wrote the plays which was said to be written by William Shakespeare. Now, scholars compare the frequency of words in books and the letters known to be written by Sir Francis Bacon. So you get the favorite words of Sir Bacon against the frequency of words in poems and the plays known to be written by Shakespeare. So you compare the favorite words between these two data sets. One is known to be written by Bacon. Another is publicly attributed to William Shakespeare. And the result is a very low probability of match. Now, we are not saying it's completely not possible for these two to match, just that the match result is a little bit low than a commonly accepted standard. So what's the conclusion? There's really no conclusion. It's a conclusion. It's up to you. But basically, that's how you do it. You calculate the frequency of words. Another thing that we all frequently do is the token recognition association. Oops, I think like the example we just used. How can Alexa, when I ask, how do I learn Java programming? How can Alexa know to come up with Professor Shen's class? Apparently somewhere inside Alexa, it treats Java programming and Professor Shen's class as two separate tokens. And these two tokens inside Alexa, she associate these two together. Of course, this is just an example I come up. This is not true. When you ask Alexa, you won't get this answer. But I'm just using this as an example. There are two tokens associated with each other. When you mention one, Alexa knows that this is the associated answer, associated term or token. So how do you do language processing? You will do document parsing first and break them into tokens. We have already done this before. You read in text files, break each row by row, break each row into words, and then you will do some data cleansing. Case conversion, all to lowercase, for example, remove punctuations, convert tokens to their original form, like if the nations becomes nation, remove the plural, teaching becomes teach, removing the tense or the form. Then you will remove stop words. Some words doesn't mean anything, like the, a, or to, something. And there are more operations that you can do. This is the part of a data science that we're not going to get a step into. For us, we are more concerned on once you get a list of tokens for each document, how are you going to work on it? You will count word appearance in the document, which is called term frequency. For example, to be or not to be. The word be or the word to appears twice. This is what we call term frequency. And the word appearance in different documents, like for example, the word be shows up in this document and the other document and the other document. How many documents does this word shows up, right? So this is how we approach the Baconian theory of Shakespeare. We calculate the word appearance in all documents, and we calculate the word appearance in different documents. The distribution of the Sir Bacon's books and letters is different from the word appearance and and document frequency pattern in the Shakespeare collections. So these two are different. This is how we approach. We do the calculation, we do the statistics, and that's how we do comparison. Then we will also build a correlation between tokens. We talk about Java programming versus Professor Shan's class. Let's use a simpler example. You also, if you're a Harry Potter fan, you probably recognize these names, right? This is all three of them, Weasley, Granger, and Potter, all shows up in all 7 Harry Potter books. While if you are a Star Wars fan, you recognize the names Skywalker, Darth. Both shows up in all Star Wars movies. These two groups of words, however, they don't show up in the same book. You look at the Star Wars movies, I don't think there's any people named Potter. Or in the Harry Potter books, there's nothing shows up as Skywalker. What you can do is you can count the appearance. If Weasley and Potter shows up together in 7 books, this is document frequency that we put here. Similarly, Granger and Potter shows up together in 7 books. This is the document frequency that we put here. Skywalker and Darth shows in all 9 movies, shows up together 9 times in 9 different documents. That's what we put here. This is the word correlation matrix, or you can call it the document frequency matrix. And we can take it further by, and you can see this is basically a 2D dimension, a 2D array. Inside this 2D array, we can put some color coding to visualize the effect. We can put the red if the number is higher than 5, say higher than or equal to 7, a little bit lighter when the number is less, and even lighter than 1, and white when it's 0. And when you have a huge set of tokens, pretty much all the words showing up in Harry Potter or Star Wars, you will have a huge map, huge 2-dimensional array. And you look at the color-coded array, you will see there are clusters here and there. Like this cluster is the Harry Potter names, and this cluster is the Star Wars names. These are the clusters that can group different things together, different concept, seemingly different concept, seemingly unrelated concepts or tokens together. If a new book come up with these 3 words, very likely it will show up somewhere in the cluster. You can also then label it as a closely related to Harry Potter. And if you think when you go to Amazon.com, you buy something, you try to buy something, you try to buy a textbook, you try to buy a Java textbook, very likely you will get recommendations like users also purchased something like this, or users frequently purchase something with this. All this comes with this technology that you build a correlation matrix, find out the cluster. And from the cluster, you can extend. Although I bought a leaf blower. Then I got a notification from Amazon that I can buy a snow remover. I never purchased anything related to that. But because apparently a lot of people buys these two together, buys leaf blower for summer, for the fall, for late fall, and the snow remover for winter. So Amazon sees I bought a leaf blower, and it considered these two as in cluster, the same cluster. So it basically makes this recommendation. This is what we call recommendation engine, and this is natural language processing. But you can see that clearly everything matters is you create, is you will parse the document, break it into tokens, create an array of a word appearance, and create a two-dimensional array of matrix. So the fancy words, fancy implementations outside those, inside those fancy implementations, deep down, we are utilizing the same thing we are learning here. These are arrays, and these are the operations of arrays.